tonight, happily. It's my pleasure to welcome you to the 2022 Caroline Herschel Prize Lecture, which this year has been given by Dr. Alexandra Amen of Cambridge University. This prize lectureship was established in 2018 by our society in association with the Royal Astronomical Society to celebrate Caroline's memory by supporting promising women astronomers early in their careers. This is its 5th year, but it's also the first year back as a live and online event after 2 years of online only by COVID restrictions. So it's great to be back, and especially in the splendid new building. I'm very grateful for many people who've helped to make this possible. They include Professor Fran Bagenau of University of Colorado in Boulder, who provided a major donation to support it. The Royal Astronomical Society, both for agreeing to be associates and for providing practical help in establishing the RAS connection. University of Bath for hosting the lectures, and especially this year in getting us back in person as well as online. And Professor Mike Edmonds, a vice president of our society, who was very helpful in setting it up and establishing the RAS connection. And Professor Claudia Harrison over there of the University of Portsmouth, and her colleagues on the awarding panel, who had the difficult task of selecting this year's winner. So you'll hear more from Claudia shortly. So why celebrate Caroline Herschel? Caroline was born, like her elder brother William, in Hanover in the mid-18th century. Unlike him, she was given little education and seemed destined to a life at home of domestic drudgery. When William came to become a successful musician in Bath in the 1770s, he brought Caroline here to join him, partly for her sake and partly for his. Here she became in turn an effective housekeeper, talented singer, and tireless observing assistant. The fame brought by the discovery of Uranus took them both south in the 1780s, and with it close contact with the King's Court. Important visitors and astronomy more than filled their days and nights. Caroline became increasingly recognized as an astronomer in her own right and received a pension from the king as the first paid female astronomer. William's marriage caused some domestic upset, but also gave Caroline more opportunities to make discoveries for herself, including 8 comets and several deep sky objects. Perhaps most importantly, William and Caroline's system of communicating and recording observations helped point the way for astronomers after them, right up to the present day. Caroline returned to Hanover after William's death in 1822 and carried on with the work of cataloguing the night sky, partly to support her nephew John in his observations. These catalogues were the precursors of the new general catalogue of deep sky objects studied in use now. I'll now hand across to Claudia Harrison to talk about the lectureship and this year's winner.
Thank you, Charles. Welcome, everyone. One of the first things that Charles asked me to address is the importance of women for astronomy. And I would like to reverse the point and say, why would women not be important for astronomy? They are relevant and important in every side of society and life, so why not astronomy, indeed? And Caroline Herschel is indeed an excellent example. And Dr. Amon, who we have awarded the lectureship, certainly so. And she will talk to us about a very fascinating and timely topic, and I leave the detail to her. We'd like to say we had a fantastic run of applicants, and therefore that Dr. Amon got this award is extremely, she should be very proud and happy because she got a unanimous vote from the panel. We did score her very high for several reasons. First of all, the presentation of the topic she would address was extremely clear and very much engaging. With this lectureship, we are seeking to award scientists, the real scientists, but with the skill of communicating science, the science that they do with artwork and supercomputer and calculation every day, also to the general public. This is something that in modern society is more and more required. It wasn't when I I graduated also when I got my PhD. The only thing we were supposed to do is to deal with our equation and the board locked in our offices. And then maybe 15 years ago, the world changed. And now we're very happy that we can indeed communicate science. So this award is not only for communication and not only for scientific excellence, but for both of them. Just a few words on the speaker. She grew up in Trinidad and Tobago. I bet those are fantastic places. I haven't had the chance to visit them. But then she studied at the University of Edinburgh. She then also got a fellowship at Stanford University. And now she's a senior postdoctoral fellow at the University of Cambridge. And she also was her PhD thesis dealing with this incredible technique that we have to measure to determine the dark side of the universe, namely lensing, got the award of the Penston Prize for PhD thesis in the United Kingdom. So we have the greatest pleasure to listen to your discussion on the dark side of the universe, Alexander.
Almost there. The lecture will last between 45 minutes and 1 hour. We'll take questions at the end. It'll be the usual roving mic arrangement for those of you in the room. For those online, please put your questions in the Q&A box, not the chat box, as the lecture proceeds, and we'll get through them all at the end. And for those online, because there are quite a few of you, you may want to put a like against one of the other questions you can see to make it more likely it will get reached. So I now invite Dr. Alex Armand to give the lecture.
Thank you. Thank you for having me. It's such a pleasure to be here to give this talk in person. Thank you so much for your kind words and for all the work that you do to make this prize possible. I really think it's important. Charles took us around the Herschel Museum today, which was extremely impressive, and I can only aspire that my notes will be as meticulous and organized as Caroline Herschel's observations, which was really impressive to see. Okay, so my job is to study the invisible. I co-lead a large international team, and we survey the night sky and harness the information from the cosmos. Are we okay? Yes, okay. And with the images we take, we make measurements, and we use them to answer the big questions. So we want to know what is out there, what is our universe made of? Why does it look the way it looks when we peer through our telescopes, and how did it come to be that way? Now, my team is not the first to ask these questions. We're really just carrying on a long-standing tradition since ancient civilizations who've looked up at the night sky and wondered these grand ideas. And, you know, we can be pretty proud as humans for the progress that we've made. We've come a long way with our understanding. We've honed a standard model of cosmology, and it does a pretty remarkable job at describing all kinds of observations. And yet, as I hope you'll see by the end of my talk, we really still have a long way to go. So you see, cosmology, like no other field, has a history of taking our views and taking our understandings and turning them totally upside down. It defies expectations. It alters the way that we view our place in the universe. And to me, that's the most exciting prospect of my work. So I'll start by going back in time and showing you a few examples of what I mean. So taking it way back, Einstein and Eddington served our first blow for the field that I'll talk about. So Einstein rewrote our understanding of gravity, the law that governs everything we know. And at the time, scientists were pretty content. So set the scene, you know, we knew that if I held an apple and let it go, it would hit the floor. It wasn't controversial. Or that if I threw a ball, I could predict exactly what speed and location it would land on the other side of the room and traverse the arc that it would travel through the sky with. Motion governed by gravity. We got it. We totally understood it. But indeed, Newton's theory of gravity, this universal law of gravitation, had stood up to every observation that we could make on Earth. And yet when astronomers started to look further afield, you know, at larger distances and more extreme environments, we started to see cracks in the theory. So for example, Newton's law couldn't quite explain the orbits of Mercury. And so Einstein proposed this new theory of gravity called general relativity. And just think about that for a second. He was proposing that we modify the laws of gravity, which is mad. Now, so his theory proposed that any object with a mass would distort the fabric of the universe. So whether it's a planet or a galaxy cluster, it distorts the very fabric of the universe, the space-time. And as a result, when we look at faraway objects and as their light travels across the universe, the light path gets bent as it travels across space-time due to the presence of these massive objects. And he claimed that if there was an eclipse, we would be able to see stars that were actually behind the sun because their light would be bent so that it would be in our line of sight. This would be the ultimate test of his theory. And so in 1919, there was indeed a solar eclipse, and Eddington led expeditions to faraway, wonderful places in the globe. And he found that this theory was right. So Einstein's theory of gravity still stands today. And yet, here were the New York Times headlines at the time. So lights all askew in the heavens and men of science agog over these observations. So general relativity is, the bread and butter of an astrophysics degree today, but back in 1919, it was a really big blow to the way we understand our universe. Now, in the 1970s, there was another point in time where cosmologists were confronted with observations by Vera Rubin that forced them to pause, to rethink their progress, and to think outside the box again. And so I'm not just talking about the fact that there's a woman in a skirt doing science in the 1970s, though we can credit Vera Rubin for totally redefining what a cosmologist looks like. But she redefined a lot more than that. She set out to study the motion of stars in galaxies. Now, the faster that stars are swirling round and round in this galaxy, the more gravity that you need to keep them bound in this orbit, to keep them glued into the galaxy's grip. So what did she expect to see? She expected that the stars at the center of the galaxy at the outer edges of the galaxy would be rotating more slowly than the stars at the center. Force would drop off with radius r, and the stars at the center would be going quicker. So the expectation was the dashed line on this plot showing the velocity as a function of distance away from the center of the galaxy. And what she found is quite strange. The outer stars shown by the data points, the observations of the data points, the outer stars were traveling much faster than the ones at the center. And more than that, all of the stars are traveling more quickly than she expected. And we can predict this. We can count up all of the stars in the galaxy and deduce the total visible mass, and then deduce the mass that you would need to keep all these stars trapped in a gravitational grip to maintain these velocities. And so there is no way that the gravity from the stars alone could be strong enough to give enough gravitational force, enough gravitational pull to prevent them from flying apart. And so her observations could only mean one thing, that there was some invisible mass in this galaxy, and we call it dark matter. It doesn't emit or absorb light, not in the optical or the radio or the microwave, but we know that it's there from the effect that it has on the things that we can see. So we know that dark matter comprises of more than 3/4 of all of the mass in almost all galaxies. And it forms this much larger, stable halo in which the light and the visible galaxy can comfortably live. And thanks to gravity, the dark matter acts as a glue to hold all the stars together within the galaxy. Dark matter is the building block for our universe, for all of the structure that we have in our universe. And it is such an important finding, and it was one that we totally weren't expecting. Now, I'll just talk about one more time when we totally had to rethink what we knew. A couple of decades onwards, humans' minds were boggled as we thought we'd understood how big our universe was. And then came these images of the exquisite Hubble Deep Field. So the Hubble Space Telescope was launched into space to take images of our universe. And this instrument is in high demand. Applying for time on HST is extremely competitive, but the director has very special discretionary time where they can point at whatever they want the telescope to point at. And people must have thought that the director was mad. So he had decided that he would use his very special discretionary time to look at nothing. So he insisted that the Hubble Space Telescope would look over 10 days at a teeny tiny patch of sky near to the Big Dipper's handle that was dark. There was nothing there. And the Space Telescope images shook our understanding again, because what they revealed is that after looking for long enough slowly collecting enough light into the telescope from that tiny smidgen of sky, the size of a grain of sand held at arm's length against the night sky. The picture revealed thousands of galaxies. So starting with these observations, we know now that our our universe is simply teeming with galaxies of all shapes, sizes, colors. And so we really had to think again about how large our universe is. So you see, time and time again, the universe has surprised us. None of these ideas were expected. Some of them were not accepted easily. And sometimes they came with wild resistance, but slowly and through the power of science and logic and reason, they were proven to be true. So I've hopefully convinced you that we must keep an open mind when thinking about the universe. And more importantly, that we have to let the data do the talking and trust the peer-reviewed science. And so now I'll tell you about one more story that I'm working on and that I secretly hope ends like all the others that we've talked about, where we get unexpected results and they force us to think a little bit harder and look a little bit closer at the data. But before we get there, let's quickly recap our understanding of the universe today. So we know that 13.8 billion years ago, the universe was a hot, dense soup of particles with very tiny density fluctuations, just random fluctuations governed by quantum physics. So some of the particles would be slightly hotter, some slightly colder, some slightly closer together than others, just randomness. The universe underwent a period of rapid expansion and it left an imprint of the fluctuations at that time. And that is captured by the cosmic microwave background. It is the first light of the universe. It is the first observation that we can make of our universe. And we have observed this. The cosmic microwave background revealed a map of very tiny temperature fluctuations and density fluctuations of the universe at that time. So Planck satellite was launched into space and it allowed us to peer back and view the cosmic microwave background. This experiment is the gold standard of our field. It delivered this map to extremely high precision. And when you make measurements from this map and compare it to predictions of our standard model of cosmology, it is an exquisite fit. It is the best evidence that we have of our standard model of cosmology, this Planck satellite observations. Now we know that the expansion of the universe marched on. So now we have time going towards the right-hand side. Those fluctuations cooled and expanded, those random fluctuations, and they seeded the large-scale structure that we observe today. So the patches of the particles that were slightly hotter formed the most dense parts of our universe. Those formed the first stars, the first galaxies, and today the largest galaxy clusters. So the exact pattern that was randomly imprinted in the cosmic microwave background has seeded what we see in the universe today. Now, when we observe, we are looking back in time. As the further away we observe, we're looking back in time, and we can see that. We can see that the parts of the sky that were most dense in the cosmic microwave background formed these biggest galaxy clusters that we observe today. Now, using our standard model, we can replicate our universe's evolution in computer simulations, like this one on the right-hand side that was built at SLAC Laboratory in the US. So these two pictures capture our universe at very different stages, from the first light of the universe to the large-scale structure that we have today. And this is the foundation of our universe, of the standard model of our universe. This model our universe is astonishingly well described by this standard model. It is a very simple model. We have just 6 parameters, and from that we can describe the evolution of our universe over 13.8 billion years. From a soup of particles to galaxy clusters and voids of galaxies. So our model is impressive. What's the catch then? Well, there are 3 components to this model. We know that everything that we are familiar with, so you, me, our planets, the gases, the stars, they make up only 5% of everything that we know. About a quarter of the stuff is dark matter, and the rest is dark energy. So I'm going to focus this talk on the dark matter side. And, you know, I do have to emphasize that it really is quite remarkable that in our insignificant snippet of time in the grand story of the universe, we can make all these different types of observations And they mostly fit our standard model of cosmology. So whether we're talking about exploding stars and supernova, or bending light, or mapping the velocities of galaxies, or measuring the first light of the universe, these measurements are very different, and they're all very well described by our standard model of cosmology. So it's an undeniable success story for our field. But there is an elephant in the room, which is that we don't really know what dark matter is. And we know even less about dark energy. And so that's pretty awkward, because I try to sell to you that we know what we're talking about, but really what I'm saying is that we don't understand 95% of our universe. And that is a pretty strange situation to be in, because despite this elephant, our model just keeps holding up to whatever observations on whatever cosmological measurements we throw at it. Our instruments and our techniques are improving rapidly, and they're allowing for more precise measurements, and we're honing our methods. So we keep throwing stones at this model, hoping to find cracks or clues or ideas for how we need to tweak this model so that we can better understand dark matter and dark energy. Now, we also know that our universe is a cosmic web. If you zoom out large enough, we see this web-like structure. There are dark matter clusters and filaments, like the black indicated in the simulation here, and they form the bones of our universe upon which the galaxies live. So in the simulation shown here, the luminous matter, the galaxies that we are familiar with, they are shown in yellow, and they live guided by where the dark matter in the universe is. It's kind of like the dark matter is this invisible scaffolding of the universe, and our galaxies are fairy lights wrapped around it. Now, dark matter does the job of gluing our galaxies together, and it is crucial to the formation of structure of our universe. So I often talk to my aunt or something, and I try to describe dark matter to her, and it really does seem like hocus pocus. It sounds like something I made up, or even that something here that we here on Earth just don't really need to care about. But the truth is that without dark matter, our universe just would not have evolved to the way that we see it today. So here are two snapshots of computer simulations I'm going to show side by side. They were set off to evolve, and one of them, the one that you can see already, is quite like our own. It has the amount of dark matter that we know exists in our universe, and it gets clumpy very quickly. It is a universe in which it's very easy to form galaxies like our own that give us stable homes for our planet. The other one has less dark matter, and not that much seems to happen. So things that start out like small clumps stay small. And so in this universe, the one that has less dark matter, you don't get anything like our galaxy or any other galaxy. So you wouldn't get the Milky Way, you wouldn't get the sun, and you wouldn't get us. And so our home simply couldn't exist in this universe. You see, our universe was concocted with the most precise recipe. There is no room for recipe replacements in this situation. So without the very particular amount of dark matter, we just wouldn't have had enough mass in the early stages of the universe to seed the structure of galaxies forming, which ended up becoming comfortable hosts for planets like our own. So we need dark matter to build our universe. And we know it exists from the effects that we can see on the effects it has on things we can see, the impact that it has. So what is it? As I said, we don't really know. Particle physicists are on the hunt for a dark matter particle. There are fascinating and intricate experiments all around the world, and we have pretty good ideas for what we should be looking for, educated guesses. But the truth remains that we haven't found the particle. And cosmologists come in from a different angle. So we study the universe and we learn about the properties of dark matter. And we use that to narrow down our list of viable models. And there are more models on the market than we can count. So some of the names are illustrated here. Everything you can think of: fuzzy, early dark matter, machos, WIMPs, self-interacting dark matter, warm dark matter. It's just not really clear that any of them fit the bill at this stage. So as cosmologists, we keep trying to describe what we know about dark matter. We can tell you where it is. We know that it behaves like normal matter with respect to gravity, but it doesn't interact with light, we can't see it, or with normal matter. So dark matter particles would fly right through us, and they are invisible. How do you learn about something like that? Well, the answer is gravitational lensing. So if we imagine a galaxy far away, as its light journeys across the universe, the light path gets bent, because clumps of matter along the way, some clump of dark matter, some galaxy cluster, it would distort the fabric of the universe, and then the light path that the light travels along gets bent. And this is a consequence of general relativity. The same idea used when Eddington proved this theory was correct when he went after the eclipse. Now that has consequences. It means that every image that we take of a faraway galaxy is slightly distorted. Its light has gotten a little bit bent along the way to our planet. And so it has, in the pictures of galaxies, the imprint of the cosmos between us and that galaxy. So galaxies whose lights travel past similar structures in the universe, like these two guys on the left-hand side here, they acquire coherent distortions or alignments. And so this is, an exaggerated effect, but you can see that they're tilted in the same way. And what we need to do is to measure that distortion with extreme precision. And then we gain an understanding about the chunk of the universe that the light passed through. So just as your glasses have a lens and they bend the light so that we have more, so that they correct the images for our eyes, it's the same idea. So that's why we call it lensing, except it's the gravity that's doing the lensing. It's the gravity due to the dark matter or clusters or some kind of matter in the universe. So the gravity acts as a lens. That's why we call it gravitational lensing. And the effect is very small. That's why we call it weak gravitational lensing. So you wouldn't see this effect with your eyes. If I showed you a picture of a lensed galaxy and an unlensed galaxy, you wouldn't see the difference. So to be able to measure this, we need tons of observations. We need heaps of galaxies so that we can detect patterns in the data. And we use weak lensing to tell us where the dark matter is. It's like our eyes can only see the light, and weak lensing lets us put on these special glasses that shows us where all the dark matter is in the universe. And so weak lensing has become a really powerful probe of testing our dark universe and testing our standard model of cosmology. And the best experiment to do weak lensing with at the minute is the Dark Energy Survey. And here it is. So the naming is confusing. Our survey also studies dark energy, but for our purposes today, let's just think of it as the Dark Matter Survey. Now, I co-lead the main team of this survey, the weak gravitational lensing team. And we have scanned 1/8 of our night sky. For over 6 years, we've taken observations. We've harnessed this information from the cosmos, and we've built up deeper and deeper images of that patch of sky. Our team comprises of scientists from all around the world, so we can no longer portray science as just a lone man scribbling over a parchment. These groundbreaking experiments require teamwork in order to change our understanding of the universe. And together, we've just analyzed half of our data set, the first 3 years of the data. And this is the state of the art in the field. So for 3 years, after 3 years of observations, for 3 more years, we tinkered over the images, we made intricate measurements of more than 100 million faraway galaxies. That is 4 times the size of the next leading weak lensing experiment. And so with this kind of statistical power with so many galaxies, we've had to fine tune our methods to be able to handle this drowning of data that we're in. And so this is really the name of the game here. So when we compare our observations of the late time universe, so we're comparing observations of galaxies and galaxy structures to the same model that is so well measured by the cosmic microwave background, then we're setting up a very beautiful end-to-end test. And so we're asking, can we use the same measurements that fits the seeds of our universe to describe the vast structures that formed 13.8 billion years later? And when we compare our observations to that CMB, we're really just testing our standard model over cosmic time. And we're asking, does our model, with all its oddities, with dark matter, dark energy, this very strange but very successful model, can it describe these 2 stages simultaneously? Now, it's a particularly exciting time for cosmology. So let me set the scene for you. Technology has rapidly grown, and with the most powerful telescopes in the world, there are several teams performing weak lensing experiments at the same time. And we're all using much larger data sets than ever used before, and we're pretty desperate to see if what we find is consistent with our standard model, or perhaps we find cracks in this picture. And our results are strange. So these are some of the headlines when we put out our results. They're not quite what we'd expect. So my first thought was, what have I done wrong? But no, I have a team that I can rely on, and still our results are intriguing. Now, what's exciting is that we see similar results from other experiments on sky around the world, hints that maybe the standard model isn't quite right. And I mean, with 5% of the universe understood, there's a lot of room to make new ground, a lot of room for improvement. So maybe our results are on the cusp of pointing to the missing piece in our model. Maybe it's pointing to new properties of dark matter. Maybe we really are on the cusp of the next scientific breakthrough. But wait, I'm getting ahead of myself. So let me take you back to the beginning. It's Christmas Day, and I'm on a short flight over the mountainous Coquimbo region to La Serena after a much longer flight to Santiago, Chile. And it's a rickety van ride across the desert, bending and climbing the 2,200 meters of Cerro Tololo. And every corner is more exciting than the last. I know what we're doing with our experiment, and I know what kind of potential we have. And up there, it is high, dry, and smack bang in the middle of nowhere. And that's just what we're after. This desolate patch of sky is one of the best observing sites in the world. For astronomers, that's no secret. In every direction that you look at the mountaintop, there is a telescope dome. And if you look further afield, there is nothing as far as your eyes can see. At the summit, this barren land feels otherworldly. There are eerie colors, it's sweltering daytime temperatures, UV warnings are signposted everywhere, and our man-made domes are just kind of scattered about. This must be what it's like when we inhabit Mars. But with all these domes around, they all pale in comparison. The Victor Blanco telescope is the king of the mountaintop. It is the tallest and it is simply gigantic. That's my colleague walking out of the observing room at the bottom. And it is the home to the Dark Energy Survey. And nestled on the fourth story of that building is our 4-meter primary mirror and our dark energy camera. Now, telescopes run under the basic principle that if you put a bigger bucket of water into the rain, you're going to collect more rainwater. So the bigger the aperture of our primary mirror, the more particles, light particles we can detect that have traveled across the universe, carrying the secrets of the universe only to be destroyed in our camera. Now, speaking of CCDs or charged coupled devices, the Dark Energy Survey camera is shown on the left-hand side, and it is also huge. So that's me standing looking up at it. It has a 3.3-foot lens, and it consists of 74 very sensitive CCD chips on a whopping 570 megapixels. So it is 50 times more powerful than the best phones in the room, but much larger, of course. And it's very high maintenance to get this going. It requires a 24/7 stream of liquid nitrogen to keep the CCDs at a healthy minus 100 degrees Celsius. But it's totally worth it because this piece of kit allows us to image a patch of sky 14 times the size of the full moon at every pointing with exquisite resolution. Now, I'm there to work, and that means that it's a race against the sun. As soon as the sun sets, we try to get as much data as possible from the universe. We're anxiously checking the time and making sure that we'll finish before the morning light starts creeping in, and then we're forced to pack up and head to bed. But observing life is pretty special. There's an afternoon meeting up at the telescope where you decide what you're going to observe that night and set the plan with the team on Zoom. Then you head back down to the lodge for dinner. And then it's a sweaty trek back up the mountain to get organized. And once you're ready to go, the observers on the mountain all emerge from their domes to watch sunset. And everyone rumors about this. Everyone comes out to watch the sun sink below the horizon. And it's pretty spectacular. And I really like this well-established tradition on the mountaintop. But humans aren't the only ones who've noticed. So the Visachas of Cerro Tololo, something like kangaroos or rabbits at the same time, they emerge from their hiding places and they gather at dusk too. So at sunset on the mountaintop, wide-eyed facing west are both astronomers and Visachas at the tip of Cerro Tololo. Now, the noticeable quiet at the mountaintop is broken a few hours before sunset as the large dome of the Blanco creaks open. And these telescopes kind of look like giants of the night sky. They're perched on the summit, and these giant robots awake almost at once, opening their eyes to peer into the cosmos. And throughout the night sky, they rotate, throughout the nighttime, they rotate slowly, taking what they can, observing from the universe and searching the skies. And we just tiptoe around them with our tiny little headlights, trying to learn what we can from our observations. Now, this state-of-the-art telescope and survey can do all kinds of neat things. So it can help you out if you've lost your car, like this Tesla Roadster that was launched into space by SpaceX. And it could let you know if you had an earthquake the night before on the mountaintop pretty clearly. But we're after something else. So what we're after is galaxies, faraway galaxies, and lots of them. So here's a stacked and processed image from the Dark Energy Survey. So remember, we have all these 72 CCDs, so that's the arrangement of them. And 14 full moons can fit in this field of view. And on a full night of observations, if you do the math, we take about 150 exposures. We point at each patch of the sky for about 5 exposures so that we can stack our image. So then we're getting about 30 different pointings and each 3 square degrees, giving 90 square degrees in one night. And in a single arc minute with the Dark Energy Survey, we measure about 6 good galaxies, 6 galaxies that they are resolved enough to do science with. And that means in one night, we measure more than 1 million galaxies of our universe in just one night, which blows my mind. The first time I tried to sit down and work out that number, I did it like 10 times because I wasn't sure if it was true. And when you zoom in on these pictures, each one of these tiny little blobs here is not a star, but a very beautifully resolved galaxy in our images. And so here are some particularly beautiful big DES galaxies. You can see that they really come in all shapes and sizes. And to do our analysis, to learn about dark matter, we need 3 pieces of information. So we need the positions of the galaxies on the sky. We need to measure the shapes of our galaxies. So we measure this in terms of an ellipticity, a 2-component ellipticity. We're measuring how lensed they are, how distorted these shapes are. And we also need to know how far away the galaxy is. And this doesn't really sound so hard. I started my PhD and I can remember very clearly my PhD advisor telling me we need to measure shapes and distances. And I was like, right, got it. But the galaxies that we're dealing with aren't quite these beautiful picturesque spirals here, but more like the fuzzy little blobs at the back. So our challenge is that we imagine galaxies like these nice ones here. But the galaxy first the light from the galaxy gets lensed, so we get this stretching, it becomes a little bit more elliptical due to the large scale structure. That's the signal we want, and that's very exaggerated here. But then, the light hits our atmosphere and our images get blurred, and that happens some more due to our telescope. And then it's pixelated in our detectors, and then there's noise. So really, we're measuring the shapes of these fuzzy blobs on the right-hand side. And even that's a really good galaxy. That would be quite a nice one. But our challenge gets harder. We can actually do our measurements perfectly, well, basically perfectly, for one fuzzy blob. But the problem is called blending. So most of the time when we're measuring light from a single pixel, that light is coming from multiple galaxies along the line of sight. The privilege of having this advanced technology and deeper data is that now we're measuring in every pixel lights from multiple sources. So one blob, fine, but what do you do with this mess? Especially when they're all at different distances. So their light is blended in all different ways. How do we measure that? So I spent so much of my time thinking about galaxies and working with them. And really the truth is that I don't like galaxies. I never wanted to study galaxies. They're not what I'm interested in. They are merely pawns in our analysis. Because what we're after is the dark matter. So with our state-of-the-art data set, we've mapped the location of the dark matter. So this is our weird footprint on the night sky, and this is a dark matter map, so that the lighter patches have more dark matter, more dense dark matter, and the darker patches have less dark matter. And this map is like when we plot our globe, we stretch it out that way, except this is the reverse, we're looking up. So the Milky Way is stretched in that arc-like shape. So this is the largest dark matter map ever made. It is 4 times larger than our competitors. And we can tell you how much dark matter there is, where the dark matter is, and show you that clumpy structure of the dark matter. But really, we can do so much more than make pretty pictures. So this is just what we use for our press releases. But we use this state-of-the-art data set to test our standard model of cosmology. And we can look under the hood at what this method looks like. So our computer pipelines, the work that our team does is really like this industrial machine. So we take our images, we calibrate them, we measure the shapes, the positions, the distances, we calibrate those, and to measure them, make sure our measurements are correct to extreme precision. And then we make statistical measurements. How correlated are these shapes on the sky? So in this patch of sky, do they have similar alignments? On this patch of sky, do they have similar alignments? And our pipeline takes our statistical measurements and crunches the numbers. Over and over, it compares our measurements to our standard model until we find the best fit for the data and constrain the 6 parameters of our standard model of cosmology. So we get a best fit value for 6 parameters of our model. And we take our numbers, our results, these are our headline results, and we compare them to the cosmic microwave background. What did Planck see? What did the CMB see? And so I thought I'd try and walk us through a graph. And so really what we're after, remember, is this test where we're comparing our measurements to the cosmic microwave background, that gold standard of the field. So on the y-axis here, we're looking at a combination of 2 of the parameters, 2 of the 6 in our standard model. And it's really just telling us how much matter there is and how clumpy that matter is. It doesn't really matter what the value is, but Planck, the cosmic microwave background, predicts this orange bar. Now, what happens when we add in the lensing data points? So remember, the dark energy survey, I keep saying they aren't the only people in the business. There's also the ESO kilodegree survey. That footprint is shown in blue. I did my PhD as part of this team before jumping ship to the American team. And there's also HSC shown in red. And our teams work totally independently, sometimes a little bit too competitively. We have very different data sets. We have very different pipelines. We basically don't really speak when we're doing our analyses. And so it's really compelling that we are basically finding the same thing. So here I've added in some of the points from weak lensing surveys, the kilodegree survey in blue and Hyper Supreme Cam is shown in red. And this is what the landscape of the field was before we looked at our results in the dark energy survey. And so there's something curious here already, right? Because we know that when we have a model and we make measurements, the measurements should fluctuate around the model. You should have some points slightly higher and some points slightly lower. And what we keep seeing is that all the lensing measurements come out low compared to the cosmic microwave background. So what is that saying? We are predicting a slightly discordant model for our standard cosmology model, a slightly discordant universe. We are seeing a universe that is smoother in structure compared to what the early universe dictates. And this lowness, these low measurements, I'm showing the most recent ones here, but that has existed from every weak lensing experiment to date. But throughout the last decade, people have been pretty quick to ask, well, what have you done wrong? This is a new technique. You know, your signal is very small and it's very difficult to extract this signal from your images. Maybe that question was fair at first, because we know that weak lensing data is challenging to wrangle with. But now we've really started to hone our methods with our enormous data sets. And with 3 teams working independently, the evidence is getting hard to ignore. We all find something different to the early universe. So when we in the dark energy survey, when we were doing our analysis, we knew that there would be intense scrutiny on our measurements and on our field. And so I wanted to really stress this point, which is that we know that we are pretty biased humans. So I am a young scientist. I'm relatively new to the field. It might be that I don't want to cause a stir. I don't want to disagree with the gold standard experiment of the field and oppose the standard model of cosmology that generations have honed before me. It's not hard to imagine that I might really, really wish that my results would come out smack bang on top of what the cosmic microwave background predicts, so that we could agree with the model and just have a really peaceful life. But that kind of human bias is really just not good for science, right? It's not acceptable. We have to be objective. And so to get around that, to get around our human bias, for 3 years that we worked on this data, we used fake data. We had entirely fake catalogs, fake measurements, fake in a realistic way. And we call this a blind analysis. So we tinker and turn our dials, we work out how best to make our measurements, how best to calibrate our data, until we are absolutely sure, and then we quickly swap it to the real catalog and hit go. And we hit go when we're on a call with 250 scientists from our collaboration, all also on the call when we unveil the results. So this is the most important presentation of your career, and you have no idea what you're going to present. It is definitely switches on the nightmares in the run-up to the big day, but all for the sake of unbiased science. And here's what we found. So the green line is what we found in the dark energy survey, the green bar. So we've used the most powerful data set. I know my team was careful. We were unbiased. And yet here again, we find that our results do not agree with our standard model, with what the early universe dictates. And in cosmology, we call this a tension. It's not quite a discrepancy. This isn't a huge disagreement, but the fact that it's coming from 3 teams is compelling. And scientists are pretty hyped about what this tension means. So what does it mean? There are 3 options. Option number 1, the cosmic microwave background measurements are not quite right. But this is the state of the art in the field. And I now work at Cambridge, where most of these measurements were led. So I definitely don't go around questioning the gold standard of the field. But it could be that the lensing measurements are missing something. Maybe all of us are making a mistake. But that's really hard to imagine, right? There are 3 teams working independently. What are the odds that we're all making the same mistake? So maybe the exciting option, we need some new physics to fill the cracks of our model. Maybe there is some dark matter property that we are not accounting for that would reconcile these observations and present a solution. And there are many voices in my head. You know, is it so bold to think that there's something wrong with our standard model? Well, let's just turn up the imposter syndrome while we're starting. I mean, who am I to question this model that has been built up over decades? But on the other hand, cosmology does have this habit of turning our field upside down. We've seen that at the start of the talk. How many times did we have to rethink what we thought we knew? And so, you know, it is the first time that we have heaps of data in this field. It's really an exciting decade for cosmology because there are just so many experiments switching online and giving us data to work with. So it really is the time to make new discoveries. And our technology is rapidly improving and allowing us to make these more precise measurements. So we will keep throwing and looking for different models. And so with our intriguing results, it's so intriguing that we're doing it all again. So as I said, we only analyzed the first half of our data set, the first 3 years. And so we're spending now, we're about smack bang in the middle of analyzing the full data set, the full 6-year data set. So we have twice the amount of data now. And we can perform an even more stringent test of our model with, we think we'll have about 200 million galaxies this time. And it won't end with the dark energy survey. The lighting isn't so good, but this is the view when you're standing at the dark energy survey and you're looking out on the mountaintop. And one mountaintop over is the Vera Rubin Observatory. And so we really are in the dark energy survey, just training ground for this epic observatory that's about to switch on next year, one mountaintop over. So quite literally on the horizon for our experiment. And Vera Rubin will absolutely change our field. So it's in a couple of years, it will switch on next year, and it truly marks the dawn of an epic era of cosmology. It will map the entire southern hemisphere. So we've done 1/8 of our night sky. It will map the entire southern hemisphere every few nights, and it will just keep doing this for 10 years until we essentially build up a movie of the southern hemisphere. And we'll stack up all of these images, getting a deeper and deeper view of our universe over the entire night sky. And so, you know, there really is no doubt that it will be game-changing for our field. The year 1 data set alone from Vera Rubin Observatory is set to have more than 1 billion galaxies in it. So, you know, think of all the measurements that we can make with those data sets. The camera is now up and running. So this is the most powerful digital camera on the planet. It is the size of a car. And it is powerful enough to see a golf ball 25 kilometers away. And it is set, ready to go, ready to deliver high resolution images of our universe or of a Romanesco broccoli, which was one of the first images that it took for the press release when it switched on. And one of my colleagues I work with who helped build the camera said he ate that broccoli for dinner after the press releases were done. And shortly after Rubin comes online, Euclid Space Telescope will launch into space, and a few more years after that, the Nancy Grace Roman Telescope. And so, space affords resolution. It gives us smaller data sets, but higher resolution, more clear pictures. And with these incredible advancements in our technology, with these 3 experiments, there are just such exciting prospects for research in the coming years. It is genuinely hard to imagine what the field will look like in a decade. Cosmologists and lensers will be totally spoiled with data. The standard model has been standard now for a couple of decades, but I think we really are at the dawn of something new, and I can't wait to see how our understanding changes. One thing is for certain, that we won't always only understand 5% of our universe. We really do have a bright future ahead to understand the dark universe, and with new, young, bright minds in the room, we'll see new ideas that will shift science. Even then, I'm sure there will be new things to learn, new pieces of the puzzle to keep on solving. So I encourage you to keep looking up and keep asking questions. Thanks.
That was a great exposition of what your work has been, how exciting it's been. So thank you for that. Questions first in the room, and then I'll go to online. We have 2 roving mics. The ladies are holding them out, waiting for you. So who's going to go first? Down there, so yeah.
Hello. You mentioned that the name is Dark Energy Survey, even though you're studying what dark matter. Is that assuming that the mass energy equivalence that Einstein proved is also equivalent for the dark counterparts?
That is equivalent, yeah. So we just, in our standard model, we expect W, the equation of state for the dark energy, to be -1, and we just test that. So, yeah. We get pretty unexciting results for dark energy, which is why I like to focus my talks on dark matter and the SA tension.
Hi, how do you image like dark matter? Like, how do you know where it is? Like, I know that, okay, it like changes the space-time, but how do you do the measurements? Like, how do you do the
Yeah,
image?
that's a really good question. So we measure the shapes and the positions and the distances to these galaxies, and then we measure these statistical measurements of how correlated shapes are on the night sky. So if we have a patch of galaxies, if we imagine the whole board has a patch of galaxies, it might be that the ones in that corner are really aligned with each other, whereas the ones down here are quite randomly orientated. And we deduce then we'll get a high lensing signal in that corner. There's a lot of alignment, and that means that their light has passed through a lot of stuff, a lot of dark matter along the way. So we would deduce that there's a lot of dark matter on this side, but not very much dark matter on this side.
Okay, thank you.
Yeah.
Thank you. Sorry for the wait. The different surveys presumably have different depth ranges over which they're most sensitive. Where do you get the strongest lensing signal contribution to your result in redshift? Roughly?
Yeah, that's a great question. So I should have said a little bit more about the other surveys. So dark energy survey really has the biggest area, which is quite nice for us. The kids survey, the European kilodegree survey, has the best wavelength coverage. So they get really accurate measurements of how far away the galaxies are. And the HSC survey has the best depth. So we get, for comparison, in every arc minute of the dark energy survey, we have 6 good galaxies, whereas HSC has 19. So they're much deeper images. So for us, the weak lensing our weak lensing measurements are most sensitive to like redshift 0.7. That's the average of the galaxies in our data sets. And for surveys like HSC, it's very different. It's more like 1. And so with Rubin, it will be more like 1 as well, or a bit higher. So yeah, very low redshift relatively.
Probably just a trivial question, but you're characterizing the sort of slight alteration of your image shape by basically squashing it and presumably an ellipticity of some kind.
Yeah.
Is that all you do, or do you do more higher order squashes as well to see if that makes any more difference?
So they are characterized in two components ellipticity. So there's E1 and E2, and it used to be our shape measurements have changed quite a lot over the years. So it used to be that you'd essentially draw a circle around it and measure your E1 and E2. But now we do more Bayesian model fitting on the images with flexible models. What we do in DS is even a bit more strange than that, but it does capture more complexities.
And does it make a lot of difference or not?
Different shape techniques have different biases. So what we used to do in the past by assuming a model was very model dependent for what the galaxy should look like and fitting that kind of shape. And they cause at the level of power that we have now, we can't tolerate that anymore. So we have to use this more flexible. What we do now is even more strange. Essentially, we take our images and we make fake images and stretch them in all different directions and see how that changes. Yeah. So we try to take into account that it's not as easy as drawing a circle around a galaxy and measuring.
Thank you.
We've got some questions online. One is from Angus Locke. You've shown just 2D images. Do you actually have a 3D model of dark matter density?
And that's a great question. And so with weak lensing, we can only tell you about all of the stuff that the light passed through as it traveled towards our telescope on Earth. So what we do in practice is that we don't measure, we don't look at all of our galaxies at once. We take our data set, if you imagine it like a volume, and we slice it up along the line of sight. So we have a block of the galaxies that's nearest to us, and then a block further away, and then a block further away, and a block further away. And we measure correlations between these blocks. So it helps us build up a 3D model of the dark matter map. The problem is that it only helps us. We can't do a perfect 3D model because it's very hard to determine how far away the galaxies are with just images. You need spectroscopic data so that you can have accurate measurements of the distances of the redshifts. So while we have photometric redshifts, it is very difficult to get a perfect 3D model. It's more of a projected effect. We can play games like cutting it up to see how it changes with redshift, but yeah.
Okay, a couple of questions about consequences, actually. One is, what do you think of modified Newtonian dynamics as an explanation of galaxy rotation curves?
Yeah, I think MOND is an interesting idea, but I think so MOND proposes this idea that maybe we don't really need any dark matter essentially. And I think that there's enough evidence on the table that dark matter exists from all different types of observations, starting with Vera Rubin's, but things like the cosmic microwave background. The problem is that our field is facing, we keep getting these tensions. So the one in the S8 parameter, the one in the clumpiness parameter that I showed is very exciting, and it's not the only one. There's a more well-known tension in the expansion rates of the universe, the Hubble tension. And the challenge that we're facing is that really there are no good models that explain these tensions. So there are tons of models on the market, not just for different models of dark matter, but also for different modified gravities. And they all kind of start to sound great. And then you test them and you realize like, oh, in that model, you can't actually form galaxies, or some major thing fails in these alternative models. And so that's really the challenge that we're facing, is that we have our model that has grounds in dark matter and dark energy that we don't understand, but it is an exquisite fit to our measurements. And yeah, we don't really have a compelling alternative right now. And I think MOND is not as compelling.
Well, Roger Moses is asking you to put a bet on your favorite alternative, therefore.
Yeah, so I've been thinking about I moved to Cambridge, where they led the Planck experiment, or were major players in the Planck experiment with CMB. And so I've teamed up with what used to be the largest critic of lensing, and now he's come on board that our measurements are correct, and we need to figure out some kind of problem, some kind of solution to this tension. And what we've been exploring is that maybe there are alternative properties of dark matter that only impact small scales that our measurements are sensitive to, these nonlinear parts of the universe. And And so that would be things like self-interacting dark matter or axion-like dark matter. They would all do that. So I guess that would hedge my bet on that.
Two more questions. One is, will studies of dark matter, dark energy also inform my understanding of gravity? Well, yes, is the obvious answer. I think you've done that one. Another one from Carlos Finor. Can dark matter change into visible matter?
As I said in the talk, we really don't know very much about dark matter. So I think a lot of things are on the table. We don't have any evidence that dark matter can change into visible matter, that there can be this morphing of one type of particle to another. Given that we haven't discovered a dark matter particle, it's not totally off the table. One thing that a more compelling, I think, thought is that whether dark matter maybe interacts a little bit with itself, with other dark matter particles, but I think it would be hard to imagine that it would change into visible matter. We would see that in our universe. There was one more question in the room.
One in the room. One in the room? So I didn't see that. Sorry. That's apologies.
I'm not a scientist, so I hope my question isn't too stupid, but when you're observing this lensing and its effect on visible light, can you infer something about, is that the volume of dark matter that it's traveled through, or can you infer something about the density of it along the way? And I guess the kind of long shot then is, you know, do you get self-interacting dark matter? Can you get a dark matter black hole? Or is that a...
Yeah, so a few things there. The one, so lensing tells you how much distortion you get as an accumulated due to all of the stuff that the light passed through. And so one challenge is that it can't distinguish between whether there was a lot of dark matter in a very small place on that journey, or whether there was a little bit of dark matter everywhere, because it's in a projected effect. So we need to combine with other types of measurements to be able to break that understanding, to tell us, no, there's not just one condensed point of dark matter, that it is distributed across the sky in this pattern. So that rules out for our observations. When we combine, we can very easily rule out things like black holes in galaxies causing this, causing the effects that we think are attributed to dark matter. For dark matter in a black hole, dark matter exists more as a halo around the galaxy, and the black hole is a very, very, very tiny centralized point of a galaxy. And so I guess in my head, the two don't. There is now evidence that very recently that there was dark matter falling into a black hole, but I'm not a black hole expert. So I think the two don't really interact. One is still normal matter.
Any others in the room? Oh, no, I'm sorry.
Don't worry. Did you need to make a particular assumption around the temperature of dark matter, which usually is assumed to be cold? And how, if you would change the temperature, how that would work towards that discrepancy?
Yeah, that's an excellent question. So we, in our measurement, in our analysis, we test the standard model of cosmology, which assumes cold dark matter as the main candidate. And in other works, we have tested against alternatives to that, like warm dark matter. And that's kind of in the camp of things that I think are a little bit compelling, because in certain types of warm dark matter, you can have something that impacts. The standard is cold dark matter. If you had some of it being warm, perhaps some component of it being warm, you would get an impact on our types of measurements and not on the cosmic microwave background. So that is kind of one that would cause changes on small scales only that we measure, that could explain the be a solution to the tension. So I think that one is still a little bit on the table, but it's very strange because it doesn't quite work. If you have fully warm dark matter, then you don't get a lot of things that we need in our universe. So what you would need to have is some of the dark matter being cold and some of it being warm. And maybe that's too strange of a universe, but the universe is quite strange already. So it's hard to rule things out. There was one more.
One more, there is, up there.
Very nice talk, thank you very much. I was wondering, so these competing surveys, there is some overlap and where they've observed, and you have the measurements of this S8 parameter, I think it was, where you can see that they agree, but you also showed some images that are produced by the desk survey, right, which kind of map out the dark matter.
Yeah.
If you actually look at the images, or if you compare the images, do they also agree?
Yeah, so we haven't done that at the picture level. So the way we make those maps are, the maps make really great pictures, but we've done this type of comparison. I think your underlying point is doing comparisons between the surveys using that overlap area, and that's really key. So we've done that type of comparison using different types of measurements. So we've taken all 3 surveys. Part of this is work that I did with a colleague at Cambridge. We took the 3 surveys in the same patch of sky and made a different type of measurement and tried to compare. And what we see is that they're consistent within the power that we have, but we're limited by the fact that we don't have large overlapping areas. So I think with Rubin searching on and doing the whole night sky, we're going to have to do these types of tests more. But certainly we're all thinking about comparing our surveys at different levels. So right now we're working on the first analysis where we're getting the 2 teams to work together, which has been quite a lengthy and political process. And what's taken much longer is that we've untangled all the things that we do differently in our modeling. We've not done the data side, but the modeling part and the impact that has on our measurements. And we still see consistency in the surveys. So it is, yeah, still. But it's interesting how many things we do differently as well. I guess that's a good thing and an interesting thing.
One more on the whoops. Thank you.
Alexandra, thank you very much for a good talk. Very interesting. I'm interested in why dark matter doesn't accumulate where ordinary matter is. You showed a radial distribution, speed distribution of stars in a galaxy. It doesn't, and the dark matter gives it the unexpected, or a graph that doesn't agree just with ordinary matter. But does that give a clue to where the dark matter is distributed? I think you said it was in a halo around the outside of the galaxy and not in a supermassive black hole in the middle.
Yes, so we can see I think the flip of what you said, but the same idea that the ordinary matter lives where the dark matter lives. So when we have bigger, even we can test this kind of thing in computer simulations, and then we can see it in our data as well, that when you have a bigger blob or halo of dark matter, usually that has more galaxies in it, whereas a smaller blob of dark matter would have smaller galaxies in it. So there is a very direct relation between where the dark matter is and then where the galaxy sits and where the galaxy grows. And that makes sense because the dark matter makes this mass and glue for things to form within it. So the dark matter forms this web-like structure, and the galaxies live kind of around within it.
A big scale. On a smaller scale, individual objects like, you know, a planet or a sun or a massive black hole doesn't seem to have dark matter in it.
Yeah, so the dark matter we can see lives we can very clearly see that it's not centralized at a center or around a planet or things like that. And we can see that, so in that curve that even in Vera Rubin's observations, if the dark matter were centralized, you wouldn't see that the things at the outskirts would be moving faster than the things on the inside. Then you would see the reverse, kind of like our sun holding things in the solar system, because the sun is the centralized mass. But this blob-like dark matter creates the measurements that are there. I hope that
Okay.
So yeah, we can chat more.
One more online. I think you've answered one of them, so I'll pass that one by. How do you think the James Webb Space Telescope may affect the search for dark matter?
Yep, I'm very jealous of everybody who works on JWST at the minute. It is really exciting, and it's really exciting to see how much it's engaged people who are not astronomers. So JWST makes very different types of measurements. It looks at the very furthest away scales, much further than things that we look at. So more looking at the first galaxies that formed and that epoch. It will tell us an incredible number of things. One thing that I'm interested in is it will tell us about this era when galaxies were first forming. So number one, it will tell us more about galaxy formation. And, you know, as I said, I didn't really set out to learn about galaxies, but now I have to learn about them more and more, because the processes that happen in galaxies like the fact that they have black holes and jets spewing out matter, they impact our measurements or the model for our measurements. And so we really need to understand galaxies to be able to model our measurements well. And I think JWST will be really revealing there. And I think it's a really key time. It's really key to learning about dark matter as well in this era where galaxies are switching on essentially. So it's very complementary to have all of these different types of experiments switching on. It really is just an epic decade for cosmology with all these different experiments. If we don't make discoveries now, I don't really know what we're doing.
Any more questions? No more online. So in that case,
I just want to.
yeah, I'm sorry.
So I hesitated because I felt a bit cheeky asking two questions.
Okay.
Are there enough cosmologists to be able to analyze all the oodles of data that you're going to be getting?
That's a good question. I think it's a different question of are there enough cosmologists and are there enough jobs for cosmology? So there are many well-trained astronomers in our field, and it is well, there is a challenge in maintaining enough people and enough good people with the number of jobs that there are. For the amount of data, we are just, in weak lensing in particular, there is a very small number of people on every, overall, it's a huge collaboration, but every little part of it. So we have a call just for calibrating the distances to these galaxies. And on that call, we're the largest experiment, and there's only about 5 or 6 of us who know how to do that part of the experiment. And so it really, and about half of them will be students who are being trained, or more than half of them. So I think one thing that we're learning, and one thing that Ruben is doing a really good job of, I think the Ruben Observatory, is hiring people who work on this experiment. It is their job to work on this experiment to help build the pipeline, because a huge challenge that we're going to have is just dealing with this amount of data. I can't take my data set anymore and put it on my laptop and do anything with it. I have to, only access it in certain ways and with supercomputers. And so I think the short answer to that question is, I don't know which way to tilt it, actually. I guess it's a complicated answer, and I think it's absolutely the right time to be doing astronomy, and it has such a unique role in science and in society. So yeah, there's always should be more cosmologists, but maybe we need to think about how our system works a little bit.
Well, Alex, I want to thank you for giving such a terrific explanation of this exciting work you're doing at the very boundaries of this mysterious dichotomy between two versions of our future. It's lots of work and lots of excitement to come, and lots of new things to come.
Yeah.
So we will follow it in the future with you, and wish you joy. But many thanks for your talk today.
Great, thank you, and thank you.